you can work through the proof of that, and then you do the same thing over here. And then you have this side, and you can get that angle in terms of that and this angle, and then use the law of cosines to get that. And that's Hobson's proof. There's also a proof in Johnson's college geometry, which takes the law of cosines and does an inversion and gets it. But again, for a convex quadrilateral. This proof with complex numbers works for a convex quadrilateral, it works for a non-convex quadrilateral. And I haven't checked the details of this, but my co-author claims it also works for a cross quadrilateral. So in Hadamard's words, sometimes the right way to do a result in the real variables goes through the complex plane. I'm not sure if you're going to be able to work this one out because you've got to check all the arguments. And some of these things are not that easy to do with the computers. Okay, so now I want to state one more geometry problem. Oh, I want to do one other thing dealing with Ptolemy's theorem. There's an Irishman named Casey who back in the 19th century found an extension of Ptolemy's theorem. I'm not going to give you the full theorem. You start off with a circle and you draw circles tangent to it, 4 of them. And then you connect the circles around the outside, drawing lines tangent to the 2 of them. And you draw the diagonals. Again, going tangent. Now use the notation that's in that marvelous book. It was published by Princeton Press, Sacred Geometry, on the Japanese Tengaku things. Was published a couple of years ago.
Sorted is something like this. They can be sorted, right?
That's a related thing, but not this, yes.
Yeah, it's inside.
Yeah, and that's also mentioned in this book. And what Casey did is to show that that's T1, 2, T2, 3, and so on. The T1, 2, T1, T3, 4 is T1, 2, T2, 3 plus T2, 3, T4, 1. And one way of proving that is to draw in this line and find a formula for D1, 2 in terms of T1, 2 and the radii of these 2 circles. You draw in a rectangle up there because these are right angles. You make this a right angle, so this one is. And you connect here and use the Pythagorean theorem, getting the T1, 2 for this, and then this is going to be R2 minus R1, and you get this side U, and then you can use the law and tie that up with this. Basically using the law of cosines twice that, this triangle, and that triangle, and getting rid of things. And the formula turns out to be T12 squared is R plus, capital R plus R1, capital R plus R2 over R squared times D12 squared. And the formula that I have here, if I've stated it correctly, when you do all of that, everything works out appropriately, and you can cancel out terms, and you get this Ptolemy's theorem for these chords is some constant times Ptolemy's theorem for the cyclic quadrilateral that we have here. You should know I shouldn't talk on things I haven't really done myself. It all works. Okay, so that's...
So this is Casey, it's not Mahagupta?
What?
No,
This is Casey. This is Casey.
So he didn't do it?
No, this is 19th century. It's basically after inversion gets started, and that's how Casey does this, but you don't need inversion, and our school teachers don't know many things before we get to inversion, and so I'm looking for proofs that I can work with teachers.
Is Casey the one who wrote the book, A Sequel to Euclid?
Yes.
Oh, it's a good book.
Yeah, and if you don't have the book, it is on the web and Google Books, and you can print it. That's what I did. Okay, I've got one more geometry problem, and this is an open problem. And I'm about ready to say, okay, it's open for anybody. For a few years, I've been saying that this is a great problem for a very good high school student, or for a quite good college student. You all know the formula for the volume of a pyramid. The area of the base times the height times 1/3. Now there's an extension of that. We take a polygon. We take another polygon in a plane parallel to it. And we connect the vertices. 1, 1, 2, 1, 1, 2, however you want to do it. You can find the volume of this by passing a plane halfway up. And you have the area of the top, the area of the bottom, 4 times the area of the midsection, divided by 6 times the height. It's called the Prismordial formula. And basically the reason that it works is that you can decompose this figure into figures so that for each one of them, the cross-sectional area is a quadratic function of the height. And this is just Simpson's rule. What, Sergey?
What is that? M is cold.
Medium, the middle. Top, bottom, and then the middle. Halfway up, you pass a plane, parallel to the initial plane. You get a figure then.
I think factor 4 is in the wrong place. When M is 0, then it's like 4.
It's 4 times the area in the middle, the area of the bottom, the area of the top. Add them together, divide by 6, and multiply by h.
Well, but when t is 0, you won't have 1/3.
Sure you do.
Okay, sorry.
This is Simpson's rule. And Simpson's rule is exact for things that are quadratic. And this, you have to figure out what the area is halfway up. And it's 1/4 of the area because of squares. And 4 times 1/4 is 1, and 2 divided by 6 is 1/3. But any analyst knows that Simpson's rule is exact for cubics as well as for quadratics. So there should be a formula like this for a 4-dimensional analog of the prismoid.
And the